Selamat sejahtera, we are from Group 3 and the enzyme that we choose is Lipase. And I am Imraj and my group members are Logashini Velayudam, Tiba Subramani, Noor Ishwari Gunalan and Angelica James. Firstly, the introduction. Enzyme technology is the application of enzyme as biological catalyst to improve industrial processes. Enzyme increase reaction rates, reduce energy consumption, and support environmentally friendly production. This technology plays an important role in industrial development and supports Sustainable Development Goal 9, which focuses on industry innovation and infrastructure in Malaysia. Enzyme technology is widely used in industries such as palm oil processing, food manufacturing, biotechnology, oleochemicals, wastewater treatment, and renewable energy production. For this project, we focus on lipase, a versatile enzyme used in biodiesel production, food processing, detergents, pharmaceuticals, and wastewater treatment. Lipase also supports Malaysia's transition toward a sustainable circular bioeconomy by improving the resource recovery and reducing the environmental impact. In conclusion, enzyme technology enhances industrial efficiency, promotes sustainability, and contribute to significant to Malaysia's economic and technological development. So for the research gap, although lipase technology has advanced significantly in several research gaps, still limit its full industrial potential. Addressing these gaps is important to improve process efficiency, reduce production costs, enhance enzyme performance, and support to a sustainable industry applications. The first research gap is high production costs. Lipase production often requires expensive substrates, fermentation media systems, and enzyme yield is also relatively low. Therefore, there is a need to development cost-effective microbial production method and optimize the production processes. The second gap is enzyme stability. Lipase is sensitive to extreme temperatures, pH condition, organic solvents, and detergents. This harsh condition can reduce the activity during industrial operations. Future research should focus on improving thermal pH and solvent stability through protein engineering and enzyme formulation technique. The third challenge is limit reusability in enzyme recovery. Free enzymes are difficult to separate from reactions mixture and are often only used once. This increases the operation cost and reduces the process sustainability. Efficient immobilization and recovery techniques are needed to improve the reuse and economic feasibility. Another important gap is the industrial scale up. Other than that, there are also sustainable concerns including the resource consumption, waste generation, and environmental impact. In conclusion, innovation biotechnology, enzyme engineering, and immobilization strategies is essential to overcome these challenges and develop a cost-effective, stable, reusable, and scale-up lipase technologies.
Good morning everyone. First I will introduce the lipase. Lipase is an enzyme that helps break down fats into glycerol and fatty acid. It is one of the most important enzymes used in biotechnology industries and many industries today. Lipase works well under mild conditions such as normal temperature and pH. Because of this, it uses less energy and produces fewer harmful waste compared to the chemical catalyst. Lipase is widely used in food processing, detergents, pharmaceuticals, biodiesel productions, wastewater treatment, and the chemical industry. Today, improvement in enzyme engineering and immobilization technology have made lipase more stable, reusable, and suitable for industrial applications. Lipase can be obtained from animals, plants, and microorganisms. Animals' lipase are found in organs such as pancreas and liver, where they help digest fats. Plant lipase are found in seeds and fruits. They help plant use stored fats during during the growth and germination. However, animals and plant lipases are not commonly used in industrial because they are expensive to produce and difficult to produce in large amount. Therefore, microorganisms are the main source of industrial lipase. Example includes bacteria such as Bacillus species, fungi or yeast such as Aspergillus oryzae and Candida antarctica. Among them, Candida antarctica lipase is widely used because it is stable efficiency and can be reused many times. Lipase plays an important role in sustainability development. One of its main benefits is that it can convert waste material into useful products. For example, agricultural waste, fruit peels, waste cooking oil, and food waste can be converted into biodiesel and other valuable products. Lipase is also useful in wastewater treatment. It can break down fats, oil, and grease found in wastewater from food industries and restaurants. This helps reduce pollution and improve water quality. Another advantage is that lipase works under mild conditions, which reduce energy use. Lipase can also help recycle biodegradable plastics such as PLA by breaking them down into smaller useful materials. Overall, lipase supports green technology and helps protect the environment. Compared to traditional chemical methods, lipase technology offers many advantages. Chemical catalysts usually require high temperature, high pressure, and strong chemicals. These conditions use more energy and can produce harmful waste. In contrast, lipase works under mild conditions and gives better product quality. One important innovation is enzyme immobilization. In this method, lipase is attached to solid materials such as silica or activated carbon. This makes the enzyme more stable and allow it to be reused many times, which reduces costs. Another innovation is mechanoenzymology. This method uses equipment such as bead mills to improve the contact between materials and increase reaction efficiency. It also reduces the need for harmful solvents. Scientists have also improved lipase through protein engineering. This modified lipase can work under extreme temperature, pH, and salt conditions. Because of these improvements, lipase are now widely used in biodiesel production, pharmaceutical manufacturing, and biodegradable plastic recycling. This innovative makes lipase technology more efficient, environment friendly, and suitable for future industries.
Good day everyone, my name is Angelina James. My metric number is CN250378. In this section, I will explain the industrial production process of lipase. Lipase is an important enzyme widely used in industries such as food processing, pharmaceuticals, detergents, and biodiesel productions. The most common method used for industrial lipase production is submerged fermentation or SMF because it provides high productivity, better process control, and is economically feasible for large-scale production. Generally, the production process consists of two main stages: upstream processing and downstream processing. The process begins with microorganism selection, followed by fermentation for lipase production, then extraction and and purification before obtaining the final lipase product. This production method also supports sustainable, environmentally friendly, and cost-effective industrial manufacturing. Next, I will discuss the upstream processing stage. Upstream processing involves the preparation and cultivation of microorganisms for lipase production through fermentation. There are 5 main stages involved. The first stage is microorganism selection, where microorganisms with high lipase producing ability are chosen. The second stage is inoculum preparation, where a starter culture is prepared under sterile conditions to ensure healthy and active cells. The third stage is seed fermentation, which increases the biomass and cell density before large-scale production. The fourth stage is production fermentation, where lipase is produced in a large fermenter under controlled conditions. The final stage is cell separation, where microbial cells and biomass are removed from the fermentation broth to obtain crude lipase enzyme. Common microorganisms used for lipase production include Aspergillus niger, Candida rugosa, Bacillus species, and Pseudomonas species due to their high enzyme activity, stability, and industrial suitability. This slide presents the process flow diagram, or PFD, for lipase production. The process starts with stock culture storage, where microorganisms are preserved under controlled conditions. The culture is then transferred to the inoculum tank for starter culture preparation. Next, the inoculum enters the seed fermenter, where cell growth and biomass are increased. After sufficient growth, the culture is transferred to the production fermenter. This is the main stage where lipase is produced under controlled operating conditions such as temperature, pH, and oxygen supply. The fermentation broth is then sent to the cell separation unit, where cells and biomass are removed to obtain crude enzyme. Finally, the crude enzyme undergoes downstream processing, including purification, concentration, and formulation before becoming the final lipase product. This PFD illustrates the systematic progression from culture preparation to enzyme production and recovery. This slide provides a step-by-step description of the lipase production process. Step 1. Stock culture storage. Microorganisms are maintained under controlled conditions for long-term preservation. Step 2. Inoculum preparation. A starter culture is prepared on a small scale to ensure cell viability and activity. Step 3. Seed fermentation. The inoculum is transferred into a seed fermenter to increase biomass before the main production stage. Step 4. Production fermentation. Lipase is produced in a large-scale fermenter under optimal operating conditions to achieve maximum yield. Step 5. Cell separation. Cells and biomass are removed through centrifugation or filtration to obtain crude lipase enzyme. Step 6. Downstream processing. The crude enzyme is purified, concentrated, and formulated according to industrial requirements. Each of these stages plays an important role in ensuring high enzyme productivity and product quality. For successful lipase production, several operating parameters must be carefully controlled. The first parameter is temperature, with an optimal range of 30 to 37 degrees Celsius. This temperature range supports microbial growth and enzyme synthesis. The second parameter is pH, which should be maintained between 6.0 and 8.0 to ensure enzyme stability and activities. The third parameter is dissolved oxygen, or DO, with an optimal range of 20 to 40%. Adequate oxygen is essential for aerobic growth and lipase production. Another important parameter is agitation speed, typically between 150 and 300 rpm. Agitation improves mixing, oxygen transfer, and nutrient distribution. The aeration rate should be maintained between 0.5 and 1.5 ppm to provide sufficient oxygen throughout the fermentation process. Finally, the fermentation time generally ranges from 24 to 120 hours, depending on the microorganism strain and culture medium used. Proper control of these parameters is essential for achieving high lipase yield, enzyme activity, and process efficiency. This slide provides a more detailed view of the operating conditions and their effect on lipase production. For example, temperature affects enzyme synthesis, cell growth, and metabolic activity, while pH influences enzyme stability and substrate utilization. Dissolved oxygen is important for aerobic growth, whereas agitation speed and aeration rate ensure efficient oxygen transfer and nutrient distribution. In addition, each parameter is monitored using specific instruments such as temperature probes, pH meters, dissolved oxygen probes, tachometers, and flow controllers. Therefore, continuous monitoring is essential to maintain optimal fermentation performance and achieve high lipase yield. In conclusion, submerged fermentation (SMF) is the preferred industrial method for large-scale lipase production because it offers high productivity, effective process control, and economic feasibility. The upstream processing stage include microorganism selection, inoculum preparation, seed fermentation, production fermentation, and cell separation to ensure efficient enzyme synthesis. The process flow diagram demonstrates the systematic progression from stock culture storage to downstream processing, ensuring efficient lipase recovery and product quality. In addition, operating parameters such as temperature, pH, dissolved oxygens, agitation speed, aeration rate, and fermentation time significantly affect lipase production and enzyme yield. By optimizing these fermentation conditions, industry can achieve higher productivity, improve process efficiency, consistent product quality, sustainable manufacturing, and cost-effective production. That's all. Thank you.
Good morning, I'm Nurishwari. I will cover the downstream processing of lipase, which prepares the enzyme for industrial use through 3 stages. First is extraction and purification. After fermentation, we separate microbial cells using centrifugation to get a crude enzyme solution. We then concentrate it via ultrafiltration, which preserve enzyme activity under mild condition. For high-value applications like pharmaceuticals, we use chromatography to achieve maximum purity and catalytic consistency. Second is formulation. The purified lipase is made into liquid or powder forms. Liquid lipase stabilized with additive like glycerol are ideal for direct use in biodiesel and wastewater treatment. Powder forms created via freeze drying offer a longer shelf life and lower transportation costs, making them perfect for detergents. However, handling powders require strict ventilation and protective equipment to prevent respiratory allergies. This ensures both product stability and workplace safety. Moving on to technological innovation. First, recombinant DNA and protein engineering have revolutionized production. By introducing lipase genes into high-yield microbial hosts, we achieve cost-effective manufacturing. Techniques like directed evolution allow us to modify the enzyme structure, significantly improving the thermal stability and also solvent resistance. Second, advanced immobilization technology is a major breakthrough. Instead of losing free enzymes after one use, we attach lipase to solid supports like magnetic nanoparticles, allowing it to be recovered and reused repeatedly. A prime commercial example is EMZYMES 435, widely used in biodiesel production for its exceptional stability and lifespan. In summary, combining rigorous downstream processing with these modern innovations drastically improves lipase quality, reduces operating costs, and supports sustainable manufacturing. This reinforces lipase as one of the most valuable enzymes in modern biotechnology. Thank you.
This slide discusses the safety and ethical consideration associated with industrial lipase technology. Although lipase offers many environmental and industrial benefits, several safety issues must be considered. From the biological aspect, workers may be exposed to enzyme aerosols and microbial particles during downstream processes such as filtration, centrifugation, and spray drying. Continuous exposure may cause allergic reactions, skin irritation, respiratory problems, and even occupational asthma. These are also process safety concerns. Lipase catalyzed biodiesel production often uses flammable solvents such as methanol and ethanol, which can increase the risk of fire and explosion. In addition, wastewater and microbial biomass generated during production must be properly treated to prevent environmental contamination. To minimize this risk, industries implement safety measures such as personal protective equipment, closed fermentation system, proper ventilation, and also immobilized lipase technology. From ethical perspective, genetically modified microorganisms are increasingly used to improve lipase production efficiency. However, accidental release of these microorganisms may disrupt natural ecosystem or transfer modified genes to other organisms. Therefore, industries should adopt sustainable practice, use alternative feedstocks such as waste cooking oil, and ensure transparency and compliance with biosafety regulations. Next is, this slide highlights the positive impact of lipase technology on society and the environment. One of the major advantages of lipase technology is its contribution towards sustainable industrial development. Lipase-based processes operate under milder conditions compared to conventional chemical catalysts. As a result, they consume less energy, produce fewer greenhouse gas emissions, and generate fewer toxic byproducts. Lipase also enables the conversion of waste cooking oil into biodiesel, which helps reduce dependence on fossil fuel while promoting cleaner waste management practice. Economically, the growth of lipase-related industry creates employment opportunity in biotechnology, biochemical engineering, environmental management, and renewable energy sectors. In Malaysia, lipase technology has strong potential because of the country's extensive palm oil and oleochemical industry. Utilizing palm oil residues and industrial byproducts can improve waste management efficiency and generate additional economic value. However, public acceptance remain important. Continuous education and transparent communication are necessary to improve consumer confidence regarding biotechnology-based products. Despite its benefit, lipase technology still faces several industrial challenges. The first challenge is high production costs. Lipase production involves multiple expensive steps including fermentation, purification, enzyme stabilization, and immobilization. Specialized equipment and high energy consumption further increase operational costs. The second challenge is scale-up difficulties. Many laboratory studies show promising results, but maintaining the same performance at industrial scale is difficult. Factors such as pH control, temperature stability, oxygen transfer, contamination risk, and methanol inhibition can significantly reduce enzyme productivity. The third challenge is regulatory compliance. Industry must comply with various regulations including environmental standards, occupational safety requirements, food safety regulation, halal certification, and biosafety guidelines. Overall, these challenges contribute to higher operational costs, slower commercialization, and more complex industrial process management. This slide presents promising future development in lipase technology. One important direction is protein engineering and directed evolution. Researchers can genetically modify lipase to enhance thermal stability, improve solvent tolerance, and increase catalytic efficiency under harsh industrial conditions. Another advancement is immobilization technology. Scientists are developing new support materials such as bicar, nanocellulose, and magnetic nanoparticles to improve enzyme recovery, reusability, and cost effectiveness. Lipase technology is also expected to support the green and circular economy by utilizing waste cooking oil, palm oil residue, and agro-industrial biomass to produce value-added products. Furthermore, artificial intelligence is becoming an important tool in enzyme biotechnology. AI can assist in enzyme design, process optimization, real-time monitoring, and predicting enzyme performance. In the future, lipase technology is expected to play a major role in renewable energy production, green chemistry, sustainable manufacturing, and industrial waste management. In conclusion, continuous innovation and collaboration will strengthen the competitiveness of lipase technology and contribute to a cleaner, greener, and more sustainable future. Thank you.
So, as a conclusion of our project report, lipase is highly valuable industrial enzyme with wide application in food processing, biodiesel production, detergent, pharmaceutical, wastewater treatment, and oleochemical industries. Its ability to catalyze reaction efficiently under mild conditions make it important tool for sustainable industry development. However, several challenges still limit its full industrial potential, including high production costs, enzyme stability, limited reusability, and difficult in scale-up laboratory processing to commercial production. Addressing these research gaps through biotechnology, enzyme engineering, and immobilization technique is essential for improving the process efficiency and economic feasibility. With continuous innovation and research lipase, technology has a great potential to support green manufacturing processes, promote the circular bioeconomy, and contribute to Malaysia industrial growth and sustainability goal. That's all from us. Thank you.